All right, good morning. Let's start. So today we'll study a little bit about what we have done earlier. Okay, in OS class, we have studied all this. However, it's just kind of revision. And why we are doing this? Why we're studying all this? Again, because we'll have to learn about one of the major vulnerability that has happened and is still happening. And it was number one cause of malware getting into systems is called buffer overflow problem. Okay, so we will study what are these buffers, so-called buffers, and for that generally it happens in the process image when you run a process. Okay, that time a lot of manipulations can happen, and then we'll study that in next 2 or 3 classes. And in order to understand that, for those who have not attended this OS course or forgotten about this concept, it will help. Okay, and also please understand that you'll have to learn x86, because in computer architecture course we have covered only RISC architecture because it needs simple, futuristic, easy to understand, and so on, right? But x86 generally it was taught some 15-20 years back. It's still taught in many universities, but it's quite complex. That confuses many of us. So it's but now with the understanding of architecture, it's fairly simple to understand the x86. Okay, so we will because you'll have to do coding, that you'll have to compile, and then that compiled code, of course, will run on x86 processor. Okay, so hence we will have to learn this. Okay, all right. So these are the references. Okay, so every class what we're trying to do is to discuss something that's related to security, and that I call preamble, and then regular topics, right? So preamble today is about breaches. What is data breach? Okay, and it's a personal data breach that impacts us. Okay, so how we define data breach? Data breaches keep happening, right? Data breach means that data is becoming available to people, or your data either is becoming is available to many people, or your data is even unavailable to you. Okay, so just a minute, we'll go back. It's a breach of security leading to accidental or unlawful destruction, loss, etc., right? So these are not only result of accidental or deliberate causes, but also because of somebody else trying to do this. Okay, all right. So for that, so if we define breaches, then we'll have to understand what is CIA. CIA is not agency in US, but it is confidentiality, integrity, and availability. Now this is a model that we'll study later. So at this point, just a minute, let me stop this. Yeah. So confidentiality, integrity, availability model we'll study later, because any system that is said to be secure has to satisfy these 3 properties. Okay, which is called CIA. Confidentiality is what? Suppose Alice. Just a minute. Suppose let me just restart it. Otherwise, my pen will not work. Just a minute. Let me just move up. Or maybe let me just up. Let me just go down. I have taken this presentation from somewhere and I never bothered to see whether it has timing. Okay, all right. So here. Okay, so we are discussing CIA model, which we'll study later. Okay, but CIA is C stands for confidentiality. Okay, let's assume that Bob is sending email to Alice. Okay. Now, okay, and of course they are in relationship, and Bob is sending some nice things, some nice things or nice worded email. Okay, and confidentiality is that if there is an element called Trudy, and Trudy also, Trudy doesn't like this relationship because he wants to have relationship with Alice for some reason. So Trudy, the Bob's email should not be visible to Trudy. Okay. Okay, so that is confidential. Whatever Bob is sending should be available only to Alice. Okay, whatever Trudy does, system should not allow Trudy to know what Bob is sending to Alice. What is integrity? I stand for integrity. Bob is sending an email and Trudy is a man in the middle. Okay, and then Trudy should not be able to change the contents of the message. Okay, say Bob, for example, sends this words, I love you. Okay, but Trudy can change that wording to I hate you. If Trudy is able to change that, it means that his integrity is compromised. Okay, all right. So we have learned two concepts. Confidentiality, it means that Trudy should not be able to even access that information. Integrity says that even if Trudy is a man in the middle or there is an element in middle, that should not be able to change the content of the message. Okay, availability is that if Bob is sending email, it should reach to other end. Okay, it should not be absorbed by Trudy and nothing should come from that, right? Even if Trudy is in the middle in the communication, right? Now, when these three things are satisfied, then we can say the system is secure. All right. Okay. So now let's get back to where we were. So CIA characteristics should be satisfied. Okay. Confidentiality, integrity, and availability. All right. So a personal data breach can broadly be classified as security incident that has affected data confidentiality, integrity, or availability of personal data, or combination of these. Okay. All right. So as long as these three do not happen, then we can say there is no data breach. Okay, personal data breach, right? So in short, there will be personal data breach whenever someone accesses the data or passes it on without proper authorization. Okay, so someone accesses the data and passes it to anybody else without proper authorization from the sender, or it could be more than that. Okay, when the data is maliciously or accidentally corrupted, lost, or destroyed. Lost or destroyed. Okay, so we'll all right. So what does it mean? Okay, or okay, we'll come back. Or if the data is made unavailable, that is by encryption by ransomware, or it's lost. All right. So now, when we say data is corrupted, lost, or destroyed, so see the data, so the Bob is sending an email and that should not be destroyed that should not be changed, or that should not be encrypted. Now, one of the ways in which cyber criminals make money is by getting into system of a company, okay, server of the company, and encrypting the whole data. Okay, they don't destroy the data, but they encrypt. Now this data becomes unavailable. Okay, and then they ask money in cryptocurrency to decrypt it, and it's happening very often, right? I mean, and there are professional companies, criminal companies that are doing all this. Okay, so whenever you want to design a system that is secure, focus on these three things: CIA. And most of the protocols that we'll study now onwards will have these three important parameters built into it. So any protocol, for example, in HTTPS that we'll study, and we'll see that what all it can provide. Okay, can it provide confidentiality, integrity, and availability, and so on, right? Usually availability is system feature. Okay, but availability should not be destroyed by criminals or cyber criminals. Okay, all right. So the question is that now, because the breaches, data is available. That's one way, right? And of course, because of breaches, I mean, cyber criminals can, of course, do other things with that available data. So now you'll have to check whether your email address has been hacked or is available in any data breach. So after the class, you go to this link and then give your email address, and you'll find out whether your name exists in any data breach or not. My name exists. Of course, my personal email address is there in at least 15 data breaches. Okay. Another question that I am asking is that if you find your name in the data breach and have not done anything or not planning to do anything, then of course you will be easy target in future, because that data is available. Your email address is available, that's fine. But apart from that, other data elements are available. For example, your date of birth could be there, your Aadhaar card number could be there, your address could be there, and these are all valuable information. Okay. Already your IP address can also be there in data breach, right? Okay, but you may argue that IP address changes every time I log in, right? Does it? Anyone? Because you don't have permanent IP address. Does it change or doesn't change?
Yes, sir, it changes.
It changes every time?
Yes, sir. Mostly, yes.
Okay, have you ever checked it?
Yes, sir, I had.
Yes, sir, whenever we reset our internet, it always changes.
No, whenever you log it out, right? Night you don't use it, right?
Yes.
And then reboot your machine. You get different IP address or same IP address?
It may be same, but it changes mostly.
Okay, yes. Good. It changes. It may not change mostly. Usually, what happens is that this your Wi-Fi router is lease period is usually small, but same number is usually given by ISP because simpler for them. Okay, so sometimes I've checked. I mean, there are of course ways to check how long your IP address remained the same. And this period could be as long as 3 months. Okay. Now, why do you get every time new IP address?
There is a pool and they distribute from the pool.
Yes, because there is a shortage, in fact, right? IPv4, there was shortage, and then not everyone uses IP address all the time. So in that pool, whoever needs it is usually given, and then it has been working. Now with IPv6, there is no shortage of IP addresses, right? So if you are on IPv6, there is a probability that duration in which IP address will be available to you could be 6 months or a year, could be. Then if your IP address is leaked, then it's interesting, because IP address is available the moment you send an email or any do web check-in or whatever, or any web communication with web servers and so on, then your IP address is there. Okay, so now your address is known in data breach. So that's interesting. All right. Okay. You'll have to think yourself how to protect yourself and your family members from data breaches, because everyone uses data. Almost everyone is online. Okay, like Big Basket, my name exists in data breach, data available through wherever Big Basket. So Big Basket, so data breach, whatever data is available in open, actually, because it's most of these data is actually sold and sometime rather becomes available, right? Then darknet is available. Okay, what do I need to do then? That's a question, right? It's available there. First thing we need to do is to change the password, change the user ID if possible, or email ID. If you have multiple emails, change the email ID. That's the simplest thing you can do. Okay. And remember that you don't need to give information as much as possible, right? I mean, whenever you create an account or something, if things are not really required, why should you give those information? Okay, all right. Okay, so now coming to something that we want to discuss today. Running of C program. I'm sure all of you understand compiler, assembler, linker, and loader. Okay. C code you write, you first convert into assembly, and then assembly instructions like, this kind of instruction, move, push, all these that we have studied in last course. Okay, so this is the first step. Of course, before this, there is something called preprocessor, something we'll show later. So this now gets converted into machine code, because ultimately machine code runs, right? So here comes a machine code. Okay, so now all right. So these are the functionalities, right? So compiler first converts to assembly, then assembler converts into machine code. Of course, in general, we can say that we can directly get A dot out. So where assembler and compiler functions are combined together. But if you give if you want, you can get assembly code through normal, compilation process. Of course, you'll have to give some, parameters for that. Okay, and then you get machine code. All right. There's nothing great about it. So now we know all this, right? Compiler, we know. Assembler, we know. Linker, what is the role of linker? Because, when you're running C program or any program in any language, there are a lot of libraries that we use. Okay, and all those libraries get linked, because ultimately your program has made a functional call to some library function. So that code should also be available in compiled form or in object code of that, and that must be merged together. And merging has to be proper such that, it should work, because, if there is jump instruction or go to instruction, it should work, because it's all relative instruction, in the sense that jumps are always relative to sum. It's usually not absolute, right? So all these adjustments about the labels must be done. Labels, not levels, right? Okay, and what is the role of loader then? Once compiled code is available, or a linked code is available, which is in object form, then loader creates the memory image, right? It's part of OS. Okay, so it sets up memory space and runs the machine code. So now the steps that are in general, we can say first is that source code is given to preprocessor, like, in top of C program, you write, a lot of, if there is a macro or hash define, etc., all these get preprocessed, and that you get a file. Then you compile it, it becomes assembly language with .x extension, and then give it to assembler and you get .o. Okay, and then linker, which will link other object files, and then you will get the code, which is a.out. Okay, simple. So at the end, we have executable file, which will run properly. Now, note that when we use word file, files are generally in hard disk, right? Or flash. Or files are static. Okay, you may change file over time, but in general, when it's non-running object, it does not have a life. Life in the sense there is no action happening around it, right? Okay, now so this object file that's available, or the file here, has got to be in a particular format. And that format that nowadays most of the system use called ELF format. Okay, ELF file format. Okay, now we are not going to study this. Okay, so for example, .o files can also be put into ELF format. Executable files which are available at the end are also in ELF format. And shared object files are also, libraries are also available in ELF format. So now, putting them together, all object file and relocatable files or .o files, and creating object file becomes easy. So we are not going to learn this because you can go through it. Okay, but I just want to tell you that this is what it happens, and then you should know it. Okay, so learn about all this if you have not done in the last course. Okay, now we have a.out available, or which is in ELF format. What is the next step? Okay, now we have executable image available, which is a.out. Okay, now this format, if you look at it, there is all these fields are there. There must be something for code, .text, which is code, and then there are some corresponding to data, which is static data, right? Okay, static data is global variable that you have defined, for example, right? Okay, apart from global variables, all other data values or something you have defined, some things that you have defined right in the beginning. Okay, all other things, all other variables are created at the runtime. Okay, now these things like global variable, etc., is called static because it's available before program starts. So it has to be in a .data area. Now anybody can tell me, if you recall, where will be other variables be? You define, say, integer int abc, and then you create, assign some values to that based on certain condition and so on. Where this abc be? Where will be it kept in memory at runtime?
Stack.
Very good. Is part of the stack. Okay. So now, so static data is there in executable image, which is in ELF format. Okay. OS copies instruction data from executable image into physical memory. And OS also set aside memory for execution stack and also for heap. Okay, so it's something like this. Okay. All right. So in order to understand that executable image is to be created in main memory, and it's created for whom? It's created for the process. The moment we use the word process is not something that comes to life. So when this A.out is loaded in the memory, RAM, and ready for execution, then we call it a process. Okay. The moment process is created, we have address space available. Okay. Address space of a process is for 32-bit machine is it's all the addresses between 000 to whatever 2 raised power 32 minus 1 is all available. And for each process, this address space is available. Not necessarily in RAM. Actually, memory location 000 should contain this, but this can be relocated anywhere based on what mechanism you are using. Generally, we use paged memory. So these virtual memory addresses, which start from 000 to some FFFF, are mapped into physical memory based on the paging mechanism. Okay, or virtual memory. So virtual memory is mapped into physical memory using paging mechanism. All right. So we have concept of address space, and you remember this, I am sure. If not, those who have not done this course, please go through computer architecture course, or maybe better is go to OS course because we have revised this concept several times, right? So we have this address space available. Now note there is a virtual address space. Don't get confused between physical address space. It's responsibility of memory mechanism or page memory, or if you are using base and bound, to put this, to map this virtual address space into physical address space wherever the space is available, etc. Okay. So now the program to process creation requires that this thing that is A.out, which is in the form of ELF or some format, ELF, all these things OS must take and put this in memory in some form. Okay, like code, static data heap, then stack will come here, right? Okay, all right. So in order to do that, it will take, it will load code. Where it will load code, there is some data area it's defined. It's called text. We'll show the bigger diagram in the next slide. Okay, then static data. Next is static data. Here it will create a small place where static data will be placed, like global variable, etc. Okay, and then it will create a stack where local variables will go, all other variables that you have defined. Okay, and then create heap. Okay, of course heap is here. We need heap because your program may want memory for certain reasons. For example, you do heap, you do malloc, and many other instructions, right? So malloc requires, and you specify how much memory you need, then that's available in heap. Okay, and then when this process image is created, or when process is created, basic files are also opened, like standard IO, input output file, like the one files that are mapped to terminal or the screen or keyboard, etc. Right? We studied that also, right? There are 3 standard files. Okay, for input, output, and error. So it also opens these files and also initializes CPU register. Now PC or program counter is set to the first instruction of the code, something here. All right, so that's it. Okay, so now layout C memory layout looks like this. Okay. Now we'll have to see this addresses. The way we will show these addresses, this is the lowest address corresponding to address space. And this is the highest address. Okay. Now, do you think that OS is part of this address space? Now, is address space correspond to a process?
Some part is reserved for OS functions.
Yes, a part of that is reserved for OS. Okay, very good. So this is a process that we have studied earlier in last course. So we have executable file, ELF file, a.out, and we create this kind of structure. Okay, so we have instruction, global data, heap, stack. Stack goes this way and heap goes this way, right? This is highest address and this is the lowest address. Okay, now within a stack we have seen when we do function call, we create stack frames and so on, right? Okay, we'll study that in the next class. Okay, so let's just go ahead. And note that program counter, which is part of the processor, points to the starting instruction of the program. Okay, so this again the same thing that we are discussing. I'm not going to go through it again. So note that stack contains local variable and stack frames. Stack frame concept we have discussed in detail in OS course, that whenever there is a function call, okay, when a caller function calls another function which is callee, then that function has to be executed. Then the variables, new variables are created. Okay, local variables corresponding to callee function, and then that's kept in new frame. And when the function is over, execution is over, that frame is deleted. Okay, please go through. Presentation and video if you forgot it. Okay, I will send that link maybe after the class. Okay, and of course this thing we have already discussed, that OS resides here. Okay, this is another view. Okay, now this is for x86. In general, so far we are talking about, this of course is for x86, but before that, almost all processors use the same structure. Now this, note that this is dependent on what? Is it processor dependent or is it OS dependent? Anyone? This structure, no, OS can be, I mean, possibly you can think of, data being somewhere else and so on.
OS dependent.
It's OS dependent, right? So if you have Linux, if Linux is running on VM, virtual machine, then even then it will remain the same. All right. Okay, very good. Okay, so now our focus is on x86. Okay, so here, okay, so we will use some terminologies here. Okay, like something called ESP. ESP is a stack pointer. See, stack always, I mean, this is one frame. If, only main program is running, and then there will be another frame. If it calls a function, the program calls a function call, then there's another frame corresponding to that function. And then a stack pointer moves to the top of the stack. Now, top here does not mean address wise, but actual in this stack, because stack is going this direction, is the top of the stack or the lowest memory address in that stack region, because memory is growing in this direction. Okay, Now, if if this function calls another function, say f2, then there will be stack corresponding to f2, and then stack pointer will move here. Okay, all right. And then we have runtime heap. Okay, now I am asking you this question: what is BRK? BRK pointer. You'll have to find it out. Okay, you can Google it, or better read some document and try to find out what is BRK. Okay, all right. So now another 10 minutes we will spend on x86. Okay, so most of us using x86. Is there anybody who's not using x86 here in the class? Or x86 architecture, which is not only made by Intel but also by AMD. Nobody, no one is using any machine, laptop that uses architecture apart from a chipset apart from that is developed by Intel or AMD. Okay, so anyone who has new Mac laptop that has come out in last 1 year? No? Okay, so latest Mac or Apple Mac laptops use chips based on RISC architecture. Okay, or we say that's based on ARM, basically based on RISC-V architecture, which is also ARM architecture. Okay, so they created new chipsets, and okay, the most of the iPads and Mac machines use new chipsets which are non-Intel based. All right, so the question is that why should we study x86? It is still the most commonly used architecture in consumer computers. Okay, and this in existence right from beginning when all this PC evolution started. First assembly language program I wrote was in 1982. You were not born even then. And for that time it was just 8085, and that became 8086 later. Okay, and then Intel was pioneer. I mean, that lot of credit goes to them to develop area of microprocessors. Okay, now 8085 was 8-bit. The processor, when we say 8-bit, it means what? Or 16-bit or 32-bit, what does it mean? Of course, address space you can say that's the address space, but register size, basically defined by register size. Okay, when we say 8-bit, it means that registers are 8-bit size. 16-bit, registers are 16-bit. Because PC program counter is also a register, and it's 8-bit, it can address between 0 to 2 raised power 8 minus 1, these locations. Okay. So when it was 8 bits, then became 16-bit, then became 32-bit, and then became 64-bit. Okay. So it has seen this journey, 8 to 16 to 32 to now 64 in over say 30 years or 50 years or 40 years, 40 to 50 years, whatever. Okay. So what is the trouble they have? Trouble is legacy. That is a strength as well as weakness, right? They can't get away with something that they developed earlier. For example, someone who has created a system program or a program or an application for x86, which is 16-bit. this application is available is in exe form, right? Executable form. Okay, or binary is available to a consumer, right? And now technology moves to 32-bit. This consumer and of course, all computers are moving 32-bit. Intel has to also sell 32-bit machines. Now the consumers or users who have bought the 16-bit program, which is executable version, by the way, has to run over 32-bit machine. Otherwise, the investment, all the huge investment will go waste. Okay. And then when they move from 32-bit to 64, it's still 16, something that's written for 16-bit architecture must run. Otherwise, nobody will buy Intel, right? If the backward compatibility is very important aspect, right? And then when they sell software, then they give some lifetime guarantee. So some, or say that how long it will continue to work. Okay. Now that is the reason that Intel has become so complex, because they have to create an architecture which will accommodate features of previous generation of architecture. So 32-bit architecture must also have features corresponding to 8-bit and so on. Okay, all right. Okay. So now as a result of that we have discussed, it has become kind of hot garbage. Because of legacy architecture that can't let go the past for backward compatibility reason that we have studied just now. All right. So, but still, the beauty of Intel is that despite all this legacy, still it is very, very popular. Okay. And they could even adopt concepts of RISC in limited way. Okay. However, overall, it's called complex instruction set architecture, and we have studied this in detail. What is difference between RISC and CISC? Okay, is ISA? What is ISA? Anyone remembers this?
Instruction set architecture.
Instruction set architecture, right? So basically, it defines instructions that are visible to developers or user, right? And below ISA is microarchitecture that's visible only to developers, or sorry, the architects who have designed the system, right? All right. So its ISA is over 5,000 pages long. All right. So ISA is very bloated. Okay. Now you know all these terminologies. Now it is little endian. It's okay. Read it about it, right? If you've forgotten. Same as RISC-V. So it's simple. Okay. Operation can use data in registers and memory. And that's interesting, right? Okay. RISC-V, if you remember, RISC-V, if you remember, there are instructions load and store. These are the only two instructions that interface with RAM. All other instructions, add, multiply, whatever. Okay, they always use both operands are available in registers. Okay, where here one operand can also be in memory. Okay, all right. And in RISC, what we have seen, instructions are of fixed size, right? 4 bytes. 4 bytes. Okay. Now, because of that, you know how much you need to move program counter and a lot of other things become very simple. While in this one, the instructions can be of 1 byte to 16 bytes long. 16 bytes long instruction, right? When RISC, we have just 4 bytes. Everything happens within 4 bytes. Okay, all right. So all this brings complexity. Okay. So please read more about x86 architecture by yourself. Okay, it's not possible for us in this class to go through in great details. you know, and there is a lovely book which is given in right in the beginning. It's written by a professor from IIT Delhi, Sarangi, Professor Sarangi. So it's a lovely book. It's available online, so you can use this to understand x86. So this diagram is taken from that book. So this is architecture, right? So this is for these are registers AX, BX, CX, DX. These are registers where you can bring data and manipulate that. Okay, this is for 16-bit architecture. Now, when this became 32-bit, then registers were EX, EAX, EBX, ECX, and EDX. The register size became 32-bit. Earlier it was 16-bit. Okay, and now 64-bit architecture, we'll see that these registers are this big, right? RAX, RBX, RCX, RDX, and then there are some more general purpose registers which are used for data manipulation, right? So now this is 64-bit architecture, and if you want to run a program that's written for 16 bits, and the assembly language uses a word called EAX, right? The data will be loaded, and this has some data, for example, it says some binary value. That binary values will be loaded here in this part. Okay, and if it's using 16-bit code, then it will load it into something that's here, this register AX. Okay, all right. Okay. Apart from that, it has some more register like stack pointer. Stack pointer size will also change from 16 to 32 to 64. So this is a stack pointer for 32 bits, and this is the stack pointer. The register is a register that's used as stack pointer for 64-bit machine. And there is something called base pointer. You remember what is base pointer?
Yes, okay. So maybe this one contains the address of, this contains the base address.
Yeah, absolutely. Yeah. Base of a frame. You know, when a stack frame starts, then it carries the base of the second. It's a little different from, I think, RISC architecture. Right? Okay, and then there are two more registers called SI and DI, or ESI and DI, which carries the value, this for optimization. It's like, for loop, where there's a repetition, is a maximum value and minimum value are stored here. Okay, will not use this. All right, and there are flags. Okay, and then there is a instruction pointer. Now, what is instruction pointer? We used this terminology earlier also.
The PC.
Yes, it is PC, nothing but program counter. So program counter points to the next instruction to be executed. Similarly, this word is instruction pointer in Intel terminology. All right. So that's all. You can find details here and so on. Okay. All this we have studied. So we can, and you see that the prefix changes, right? AX for 16-bit and put E is extended. So it becomes EAX. And then this prefix changes to R. So it becomes, register name becomes RAX. All right. So this how they have named it. So R prefix and E prefix for 64 and 32-bit registers. E for 32. This is for 64. All right. Okay. Please go through it. All right. And then please read the assembly language by yourself. Okay. For example, we use this percentage sign when you name a register. Okay. And then immediates where we actually use the values, then $sign is used. Okay, in the instruction. All right. Then the offset, we say that something that's pointed by register is say 8 bytes away from the value in the register. Okay, so there is a register ESP. This points to it has some number. Okay, it points to a memory location here. When we say 8, then it's 8 byte away. So this value becomes then, this value then becomes the location somewhere here, or it points to a byte which is 8 bytes away from ESP, right? We have studied this, right? So this is the way we do it. Okay. Now most arithmetic instructions are register. Of course, register is like add A, B, and so on, right? Both values of an operation like addition, etc., are available in register. Or one can be in register, other can be immediate. Okay, like for example, add A10 or something like that. Or it could be register memory. One operand can be in memory, one can be in register, and that's not possible in RISC. Or it could be memory immediate. That's very interesting. It means that both operands are not in register. One is in memory and another is immediate or actual value. Okay. All right. Okay. So examples are here. Okay. Now add L. L stands for, we have mentioned somewhere here, 32-bit, I think. 32-bit, yeah. This 32-bit instruction. $X8 and EBX. Now note that in RISC we have 3 registers, right? That we define 2 source and 1 destination. Okay, so understanding becomes clear. Now here implicitly we say 1 register which is destination is also source. Okay, so it means it's confusing, right? So now EBX, this destination, is the value that will be stored in EBX is the earlier value of EBX, whatever value is there in EBX, add to this something that's there in register X8. So this value and this value is added and then stored in register EBX. Okay, so it's a different way of doing programming. So once you do a little bit of programming, you get used to it, right? All right. So that's it for the class. I would think that I will not go through assembly language programming of x86, but it's a good idea to go through the book and learn a little bit of programming so that you have a feel for it. Okay, and because we will use this in buffer overflow problem, or otherwise is also good to know. Okay, any question up to this point? Okay. All right, let's move ahead then. So to summarize, we have in the beginning, we have looked at data breaches, and proper definition of data breach happens when we understand CIA. We can say data breach happened because one of these conditions have not met. Okay, so now availability of data is another important aspect that cyber criminal can decrypt our data, encrypt our data, and data becomes unavailable. Okay, or because of breaches, our data becomes available to everyone. So confidentiality is lost, or data can also be changed. Okay, then integrity condition is not met, right? So basically breaches can impact all 3, CIA. Then we looked at how program become process, because we wanted to understand the concept of process image. And process image, we have seen it has multiple sections, and section that will be interest to us will be stack and heap. And we have seen that when main, for example, when you write main in C, it creates, when it's running, it creates just one stack frame. And when main calls another some function, then another stack frame corresponding to that function is called, and that frame calls another function, then another stack frame is formed. And these frames are also destroyed or removed when function finishes, right? All right, and then we have looked at some aspects of x86 architecture. All right, that's all for the class today. Thank you. Bye.
Thank you, sir.